Hello everyone, my name is Dharamveer Kumar and I'm a PhD candidate at IIT Bombay, and today I will be solving assignment 4 of the real analysis course of NPTEL. Okay, so if you have any questions you should ask me now. I will try to solve them. Any conceptual questions, or if you don't understand some topic or any specific question from the assignment. So if you have, you should ask me now. Then I will solve it and then I will start with the assignment. Okay, so I'll go with assignment 4 then. Just one second. Yeah. So assignment 4, I'll get started. So this is question 1. It's a true and false question. Okay. So let me check once the recording is okay. Yeah. So yeah, it's a true and false question. The question is, the image of a closed set under a continuous function is closed. It's asking the image of the closed set under a continuous function is closed. It for the pre-image, yeah, it's definitely true, but the image, not necessarily. Okay, for compact sets it is true. So we'll give an example. Okay, tan inverse from R to R. What is the image of tan inverse R? It's nothing but minus pi by 2 to pi by 2. Not closed. Okay, just one second. Yeah, this is not closed, so we get that. It's not important. Yeah, it's not important for it to be closed. It's not necessary. Okay.
Shall I ask it though?
Yeah, sure.
No, actually, when we were defining the function, right, at that time, function will map interval to interval, right? Then, if it is a open or closed interval, that image will be interval only, right?
But R is not an interval, right?
Here,
finite interval.
okay.
It's not a closed.
Here,
yeah, just one second. Yeah. Go ahead. Again, tell me. Just one second, right?
Yeah.
I don't know why I'm hearing from two devices. I'm speaking in this. Able to hear in this. I don't know what's happening. To speak in this. Okay. Just 1 second. Yeah, Karthike, go ahead, speak. Yeah, basically R can also be an interval. It's not breaking. So what are you saying? You're saying that? Yeah. It will map. Yeah, it is mapping interval to interval. No, why? No, that is not necessary. Yeah. Yeah, but R is not a closed interval. So, so we close set. So you have to give this for a general. Yeah. So, but if you have a question, the image of a closed set, it will be closed. Yeah. Because so if you have F interval, this will give you interval, right? We don't know what it is. Okay. Now, if this is a closed interval, um, just wait a second. So this is some interval. Yeah. So if F is defined on all of R, okay. Let's say F is like this, okay, and then you have an interval, closed interval. Okay. Let's call it A. Then R of A is open. Now we want to understand what F of A is. We know that this is an interval, right? Now what we don't know, this, okay, so this is, so F of A is an interval, R of R of A, right? So now if you apply the continuity, you have to apply continuity, okay. So but this R of F of A. Yeah, we cannot say that. Just 1 second, yeah. Check. I did this in last class, right? Yeah, so that's what we did. If I is in R and for a closed interval, it will be a closed interval. Yeah, I think we did this in last class already. Okay, so I'll move on. Question 2. Yeah, so I think, yeah, I'll just let me write it. So F inverse of a complement. So like if, let's say you have something like this. This is F inverse A complement. So this means F inverse F A complement. So if F of A, and then we are taking a image on it, so this will be and which is open. So hence this is open, so this will be closed. But this is for an invertible function. I have done it for now, just an example. Okay, so you have to follow the general procedure that we did in last class. So how to get the interval to interval. Okay, so again there is a true false question. Let f and g be continuous. We have done something like this before. Whenever you have something like max of fg and min of fg, are these continuous? Okay, so we have done something like this. Whenever you have max and min and you don't want to get into max and min, right, what you do is max of fg, always do this. Mod is much easier to deal with. That's it. So if f is continuous, so let me so we have to note few things. If f and g are continuous, that implies alpha f plus beta g for all alpha beta in real number are continuous. Okay, and another thing, so we need two statements. Another thing, we have done this before, but I'll do it again, that if f is continuous, that implies mod f is continuous. Once we do these things, first you do f minus g, from here it is continuous, then mod is continuous, so this function is continuous, you are adding again two functions continuous, multiplying with something continuous. Okay, similarly over here. So very simple. Alright, so what do we have is for every epsilon greater than 0 there exists a delta greater than 0 such that what is the definition of a function being continuous, right? So it matches open set with open set. So at a point x, if you want to say in real numbers for all y, such that x minus y is in delta, implies so if f is continuous, you want to see for what happens with f plus b, f plus g, let's say, right? So you do this. You take epsilon by 2. So basically you have to use this. This implies so from here call f plus g is equal to h. You can do pointwise definition, right? This means h of x minus h of y this is very simple. Now again, if you want to do if you want to add like multiply alpha, right? So again define h is equal to f of alpha. So now we have for any arbitrary alpha, that's alpha is given, right? You define like this, E alpha. So from here, because let's say you had this, right? Choose epsilon to be this. So from here, this will imply rather mod alpha. So for any alpha in R, and whenever you add, both are continuous. Now, what about mod f? So let's say, so you want mod fx. You want to say something like this, right? This eventually. Do you understand why this is true? Basically, this is this identity. So first try how to do this is you first take triangle inequality in this direction. This is a triangle inequality. This is also a triangle inequality. How do you see this? From here. Adding these two should be greater than this. This comes from, this is a triangle inequality, you get it in this form, right? And now let's call mod A minus mod B as K. This is K minus K, A minus B. What does this imply? That A minus B is bounded by mod K. Just think that. So yeah, this is the trick that we use for mod, and I think we are done. Let's go to question 3. Then f is uniformly continuous. So if you looked at the definition over here, and this is very important to understand what is uniform continuity. Okay. So whenever we are for a given epsilon, when we are choosing delta, this delta depends on this x over here. This delta, it depends on x. For each point there is a delta. That's how you define continuity, point-wise continuity. And when you say a function is continuous, it's continuous at all points. So for given, you give an epsilon, right? This delta changes from which point you are evaluating the continuity, from which point you are checking the continuity. This delta that you will find changes from point to point. But for some functions, it does not. And those functions we call uniformly continuous. Okay, so we want to solve this. So for every epsilon greater than 0, there exists a delta which only depends on epsilon, such that this is true for all x and y, such that I'm just writing epsilon as a subscript, so like just to say that delta only depends on epsilon, such that fx minus fy so let's say this is true, right, for all xy in R. So we are done, right? All I need to do is fx minus fy if this is delta and this has to be epsilon and this is delta, all I need to do is d bit, so delta, that implies delta is equal to epsilon over 1 over beta. So if you give me an epsilon, so let's say give an epsilon greater than 0, choose delta is equal to epsilon 1 over b. So you reverse engineer it. That implies, since beta is greater than 0, this implies, right, now for all x and y such that x minus y is less than delta implies x minus y beta, beta, and this is given, this is given, and that implies, so for a given epsilon greater than 0, I have found a delta only dependent on epsilon. It also depends on beta. Beta is a parameter. It doesn't depend on x or y. This is what they're asking. So hence you can call it. If you have any doubts, please ask me. It's very, so like if you go forward, you will learn about uniformly equicontinuous. So you should always be clear what we are talking about. You will learn about point-wise convergence, uniform convergence, and stuff like that later for sequence of functions. You should understand what kind of continuity one is talking about, and it needs to be crystal clear. So a subset, again, it's not an interval. A subset is defined to be convex if for any xy in a, simple, right? Simple definition, it's like a line. One and 0 are redundant because if x and y are in A, if you put t is equal to 1, it will just be y. T is equal to 0, it's just x. So they are always there. So it's redundant 0 and 1. So what it means is, if you have a set could be bunch of intervals, it could be, there are points and everything. What it means geometrically is, if I take a 2-point in set and if I join it, they should all lie inside the set. So this is not convex because these are the points on the line joining it, and they are not inside the set. Let's say if this was the set. So I hope that is clear physically what it means. The question is, convex set implies interval. Converse is false. Interval implies convex set. Converse is false. Convex implies interval, interval implies convex. None of them. how do we define interval, right? How do we define? Leave the infinite intervals. Um, if you have like, so these are the examples I told you, right? So over here, either this or this, infinite intervals. There is also like minus infinity to infinity. These are the examples of interval from left hand side. From right hand side, they can be a to infinity or a to infinity, or yeah. These are the 5 infinite examples. Other than that, they're of the form AB. It could be closed, open from both sides, or like closed, open, closed, closed, stuff like that. What it eventually means is, so if you have a point, if you have A and B, right, and there is X, so it can be, there could be equality, there could not be equality, right? So if you have some point X, so I have to show that this is convex, right? So now if I take 2 points inside an interval, okay, if I take any 2 points inside an interval, let's say A, B is in the interval, right? So interval has if it is this form, right? Or so let's say we can do x, y, right? That means x and y both are greater than or equal to 1. There could be non-equality as well in for general case, and xy could be something like this. And this implies that tx plus 1 minus ty would be about less than equal to greater than equal to this thing. That implies when you sum this up, so tx plus 1 minus ty is inside A and B. Hence, and it's inside the interval, right? If this was a set, interval was a set, then hence for all t in 0 to 1, tx plus 1 minus ty is in I. So basically I is convex. So this is wrong, definitely. Now let's say there's a set A, let A in R be convex. So now consider A and B in A without loss in generality, A less than equal to B, and let C in R be such that so for any point A and B, so you can find a T such that, so you can find T such that this implies that C is in A. So given any 2 points, this C inside A. This cannot be applied to the infinity cases. So for infinity, like, so let's say real number, right? So real number is convex and is an interval. So this case is sorted. It's very easy to see. If you take 2 points, whatever you do, it will be a real number, and R is an interval. So yeah. So for R, except R, this is valid everywhere. No, question 5. Twin false. Again, it's talking about open set, not open interval. So there's a function which is continuous and there is a set which is open. So it's asking, is f of u open? Again, it's not talking about open interval or anything. It's talking about general open set. So very simple example. Fx is equal to 0 or fx is equal to some constant. Right? So f of r is equal to this set. This is open, this is closed. Same argument as before. So in general, if a function is continuous, it doesn't map open set to open set. It doesn't map closed set to closed set. There is something called open mapping theorem. There is a specific case when this will happen. Okay, there is it has to do with subjectivity and everything. I don't remember exactly, but yeah, something like that. It's called open mapping theorem if you want to look it up. So now there's question 6. Let's do this. Let K in R be non-empty. Let f from K to K be continuous such that, this is interesting, fx minus fy is a non-empty set in R, and you're taking function from this K to K. Then which of the following is true? This is an interesting question. F is 1 1 in F inverse of F inverse is defined as fk to k is continuous. If there is 1-to-1 mapping, you can do this, right? So you have to check subjectivity and everything. F is 1 1, but F inverse defined from, so is not continuous. Okay. C, F inverse from fk to k is continuous, but this is a little oxymoronic statement. This cannot be a function otherwise if it's not 1-to-1. D, none of the above. The solution. Okay. So what it's saying is there is K, there is F. So when F matches, it may not be in general surjective, right? So there's a set called Fk. Definitely Fk is inside K. Okay, you can do this. So you can always do this. Fk is inside K because F may not be surjective. Now it's asking, is it 1 to 1? If it was not 1 to 1, I'm not using this property yet, I'm just saying in general, if these are 1 to 1, what you can do is you can define this. Why? Because if it is 1 to 1, let's say if it is not 1 to 1, okay, let's say there are 2 points which is going to 1 point over here, right? So now if you define F inverse from Fk, okay, this point will be in Fk to K. There will be 2 points, not a function. If it's not a function, how can it be continuous? So this is wrong, definitely. We just need to check if it is 1 to 1 first, and then also if it's continuous, otherwise it's none of the above. So yeah, so to check 1 to 1, what do we do? Just simply, you want to understand something like this, right? You don't want this case, you want this case. So what you are saying is, you start with 2 points. So let's x1 not be equal to x2. This implies f of x1 not equal to f of x2. This is this case. So there are 2 distinct points. The function will also be 2 distinct points. And f is continuous. Okay, you cannot always, for every continuous function is not 1 to 1 for sure, right? Like for example, x square is not 1 to 1. So for continuous function, you have to use this property as well. Okay. So we have this f of x minus f of y pick x1 not equal to x2 such that x1 x2 is in K, because the domain of K is f is K only. Okay, what does this imply? That x1 minus x2 mod is not equal to 0. Then what is it? It's mod, it will be positive. That implies this is positive. Substitute that in here. So that implies f of x1 minus f of x2. If something is, if a mod of, so you know this, right? If mod of x is strictly greater than 0, right? That implies x is not equal to 0 for sure. If it was 0, that there will be an equality. Okay, hence f of x1 not equal to f of x2, hence 1 1. Okay, now we have to show that f inverse. So now we can define f inverse very nicely. So f inverse will be from fk to k. And since it is from one side it is 1 1, from the other side it is also 1 1. Okay, this is a good function. This is also surjective. It's touching all the values. It's also 1 1. Basically, this is a whole bijection. Since this is a bijection, you can define its inverse. So basically, if you say that f from k to fk, it's f inverse inverse, you can define from k to fk. This is also a bijection. Note that f from k to k is not a bijection because of it's not a surjective function. But these two are because of the way we have defined. Okay, now we want it to be continuous or not continuous, we will have to see. Okay, so if I check f inverse of x minus f inverse of y, taking 2 points for x, y in f of k. Okay, and f of k is inside k. So if you have 2 points inside k, okay, what can you do? So f inverse of x, right? So f inverse of x is also, so you give me a point in fk. F inverse of x is in k, and this is also in k. This is some point in k, this is some point in k. What do we have in k? This property, x1 minus x2 less than equal to f of that. So you take f of f inverse of x minus f of f inverse of y. Because it is one on one, right? This is nothing but x minus y. And this is true for all x and y in f of k. Now pick an x naught in f of k, leave everything. Okay, we directly use can we just 1 second. So for a given, so you have like this f inverse is a sum function g. So let's call this g. Okay, g is 1 on 1, is a bijection from a to b. It's a bijection. Okay, such that g of x minus g of y is less than equal to x minus y for all x, y. Can we do this? Can we show continuity? We cannot, because A could be a closed set. At this point, we don't know how to define continuity. It's difficult, if you understand my point. You have to define it sequentially. There's another thing that I missed over here is, till now we don't need anything. From here we'll need, let K be compact. I'm just seeing if it's equicontinuous or not. Because we read that if A and B are R, and if this is true, we are done. But now this is not R. Okay, you have to be a bit careful. You cannot define x minus y. So all x minus y may not be in A, or something like that. Okay, just you have to be a little bit careful. For example, if you have a compact set from 4 to 5, if you are taking a difference, the difference may lie outside. If you want to take, like, for this point, let's say, right, for x naught, so you want all the points x naught minus y such that this is for any delta, this will come over here outside the set. For that you cannot define this. So what do you do in that case? You define sequentially, or you define from continuity from the left hand side or the right hand side. So when it is compact, right, it is closed and bounded, definitely. Okay, so since it is closed and bounded, we'll have to define it sequentially because it's not an interval as well. So it's a better solution is define. So what do we do? How do we define sequentially? If xn converges to x, then fxn converges to fx. That is the definition in terms of sequences. So let's pick a point. X naught. Just 1 second. Yeah, okay. Sorry for the disturbance. Yeah. So now let's pick a point x naught. And then you can define this thing. That's why I just wanted to introduce like sequential continuity. This is how you do it. So if xn converges, so let's say there is an xn, any xn which converges to x naught, any xn. You cannot just show for one sequence. So all the sequence that converges to x naught, you have to show this. Right? So let's say if there is a sequence which converges to x naught, that means for all epsilon greater than 0, there exists n natural number such that xn minus x naught is bounded by epsilon. But xn minus x naught for the same n, what this means is, and then xn, all the xn's basically, this belong to the set f of k. So when that happens, you can write it as f inverse of xn minus f inverse of x naught from here. From here we are writing this down. So that implies f inverse of xn converges to f inverse of x naught. You understand what I said? K was compact. So let's say, for example, assume it is an interval. We cannot define it as our regular thing because whatever we define continuity usually, this was an open set. It was an R or some open set. So when it is a closed set, you define it sequentially. So it's easy. You don't have to do left, right. Any sequence which converges to x naught, which lies inside fk, you can do this. This is called sequential continuity. For your cases, For in real numbers and everywhere it is equivalent. It is equivalent on any metric space, by the way. Okay, so this is a new question talking about connectedness. Q is disconnected in R. What does disconnected means? If you take a 2-point, at least one of the point will not lie in the set in between. So the solution is, this is true statement. Solution is, we know that root 2, we have proved that it is not a rational number, right? So now you take a set A which is minus infinity to root 2 and B equal to root 2 to infinity. So this A and B are what? Open, non-empty and disjoint, right? They don't intersect, they disjoint and everything. But A union B intersection Q is Q only because A union B is nothing but R minus root 2 and intersection Q. So if you remove root 2 from R and you just intersect, you actually get all real rational numbers. So hence Q is disconnected. Basically, if you have to show that a set is disconnected, what you have to do is you have to take two sets, disjoint sets, such that this is true. For example, like this set, if you have an interval like this, two intervals, right? This is disconnected. How? You can basically take a point over here, right? Simple. And then a point from here. Let's say this is a point A. Again, same thing, minus infinity to A to infinity, open, non-empty, disjoint, A union B, and let's call this capital, no, let's call this C. So A union B intersection C, A union B was R intersection C is nothing but C, R minus A, sorry. So hence, again, so this is the idea of discontinuity, like you want to go to an interval, like an interval is a connected set. So you want to generalize the idea of connectedness through an interval, like so through a connectedness you want to generalize the idea of intervals. This is the last question of today in assignment 4. No, yeah, hello. Yeah. So this is the definition of disconnectedness, if you want to show disconnectedness. So what we are saying is, if I have two distinct intervals, right? And if this is a point which is not in this, like let's call it C1, let's call this C2, and let's define C1 as C1 union C2. This point A is not in C, right? I'm trying to give you a visual representation of what is called disconnected. This is disconnected, right? You prove in the same way. Minus infinity to A, call it A, call it B. A union B is what? R minus A. And A does not lie in C. So if you take an intersection with C, this will be nothing but C. Same thing, open, non-empty, disjoint, A union B intersection C is C, hence this is a disconnected set. But if you cannot do this the same with the interval. So the interval is a connected set. So what you're trying to do is, with connectedness, you're trying to generalize the idea of an interval. Okay? I hope you get this. Okay, so before the last question, let me just save the recording once. Yeah, so we are back. Just give me a couple of minutes and we'll start again with the last question. Okay? Okay, so I'm back. Let's do question 8. Find let f1 so this is well defined. Which of the following is true? a good question. It tells you about the boundary points of interval. That is very important. It's a very fine distinction between a closed set and an open set. And these are the things that makes you realize that one of the example is if you have an open set, right? A continuous function, if you have a continuous function, right? It's just because it's open, there could not be any maxima. I can define something like a tan x, right? Example of a tan x function. It can go up to infinity. But if it was a closed set, any point you have to take inside this, right? For any continuous function, there will be a maxima and a minima. You cannot take outside because then there will be a discontinuity of tan x. But yeah, it's very important to understand. That is the extreme value theorem, right? There is a maxima and a minima on a compact set, or for simple example is a closed and bounded. There's always a maxima and minima. We'll do that. I'll tell you. We were talking about the closed interval is a closed interval, right? A function, continuous function maps a closed interval to a closed interval. We'll do that. Okay. So, first of all, uniform continuity. So, what do you want in uniform continuity? Something like this. So for every epsilon there exists a delta, so that for all whatever set, right? So what we are saying is you can define a function from R to R. This is fx is x square. Now if you restrict this to 0, 1, then it is equicontinuous, or 0, 1, then it is equicontinuous. That's what it's saying. But outside that, it is not equicontinuous. So we need to show all of these. Moreover, if f is uniformly continuous on a set A, right, then definitely if for a set B, let B be not be phi, right? If it is uniformly continuous on a bigger set, then definitely on a smaller set also that everything was true. Now there's a statement you need to note that so how do we show this? Okay, so we know that f is continuous, right? F of x square, this is continuous. So let's say some continuous function. You pick a point, pick some x naught in A. Let f be defined from some A to B. You pick some x naught in A. We don't know A is open or closed. I've told you sequential continuity, right? That means there exists, so for every epsilon greater than 0, there exist n in natural numbers such that let this be true. Fix an epsilon greater than 0. So let fix epsilon greater than 0. Then let there exist n. So let xn converges to x0. And xn is in A. Okay? The whole. So for all xn which is in A, let's say this is true, you pick one of them. This, since it's continuous, we know this is continuous. F of x is x square, right? That means I'm not going to prove that for now. That implies I'll write in simple terms. Remove all that. Pick x naught in A for all sequence which in A such that if xn converges to x naught, that implies that fxn converges to. It doesn't require open set, A to be open, closed, whatever. Now let's say let A be compact. This means A is closed and A is bounded. Okay. Now pick 2 points. So pick 2 points, x naught and y naught, and then x naught converges to x naught and yn converges to y naught. Okay. In A. Okay. And since these are continuous, that implies fxn converges to fx naught and fyn converges to fy naught. And then we have to show that it is always uniformly continuous. Right? So now I pick one epsilon. Okay. What we can do is adding these two. That implies we can change this to this from triangle inequality mod minus x naught minus y naught. And then xn minus yn minus epsilon 1 minus epsilon 2 from here we do opposite. Epsilon 3 plus epsilon 4 is bounded by, if you just sum this up, xn triangle inequality, but this time split in the other way around. So this is fx naught minus fy naught all you have to do is, now this is the case, right? And if I show this to be true, then I'm done. All I need to show is this to be true. Okay, so now from here, if this is clear, everything is clear, from here what we can show is we can choose this appropriately and then we can show this to be true, or rather, okay, we will not show this, rather what we want to show is leave this. Leave this. And add them. Actually, do the opposite. My bad. Now the set is bounded because it's compact, right? So it will be xn minus yn, no matter what they are, this will be bounded by k plus epsilon 1 plus epsilon 2. Since it's compact, by extreme value theorem, there exists a maximum and a minimum. This will be bounded by f max, f min. F max minus f min. A positive number. So from here we can say, we can talk about uniform continuity. Let's do, I'll do this, I'll come back to this. First I just want to talk about why it is not continuous on uniform continuous on the rest of the space. Okay, so pick any x in 0 to infinity and n in z plus. Okay, take mod of that, right? So whenever you're taking some point x in positive, and you're taking x plus 1 over n, right? And x square is an increasing function. The x plus 1 over n is obviously bigger. What is this? F was x square, right? This is nothing but 2x plus n plus 1 over n square. Okay. Now 1 over n square, n is from 1, so this is definitely 2x plus 1, 2x n over n square is definitely greater than 1. This implies what? 2x plus n so 2xn, sorry, this implies 2xn plus 1 over n square is greater than 1, which implies 2xn plus 1, this is x, n square. Hence, this implies, because n is greater than 1, n square minus 1 over 2n. So you take fx plus 1, something like this is greater than 1, then x is greater than n square minus 1 over 2n. So now take any delta greater than 0, it means there exists n naught in z plus such that this we have done, right? Any delta greater than 0. If delta is greater than 1, then for all n naught this is true. If delta is less than 1, then also we can do it, because it will be 1 over delta greater than natural number, Archimedes principle. This we did it, right? Now from here what you do is choose x naught is equal to n naught square minus 1 over 2 n naught. This is x. So now what you have is x naught minus x naught plus 1 over n naught is equal to 1 over n naught, which is less than delta. And what about this thing? This thing we know is f of x naught minus x naught plus 1 over n naught this was greater than 1. Right? So you are taking 2 points based on n naught. So you have taken x naught, some x naught greater than this, and then you are taking some n naught, and you are showing that this is greater than 1. It cannot be, so it cannot be valid for any epsilon, right? Do you understand my point? Let's say you give me some epsilon. Okay, then if I choose x is equal to x naught and y is equal to x naught plus 1 over n naught, where n naught is given by this. if there were delta, if there existed a delta greater than 0, such that x minus y is less than delta for all xy, right? And that would have implied that f of x minus f of y is less than epsilon. Okay, so I have picked epsilon is equal to half, for example. Now, no matter what delta you choose, I will always find a point xy such that x minus y is less than delta, but this cannot be satisfied because we have already done this. You understand my point? If I choose epsilon is equal to half, now what we wanted was, if epsilon was half, delta, there will be some delta greater than 0, that such that this is true for all x and y. But I'm saying no matter what delta you choose, there are these points x and y such that this cannot hold. That's the point of that's why it's not uniformly continuous. That's the case where the uniform continuity comes into the picture. No matter what delta you choose, I can always find 2 points x and y such that this is not valid. And where am I finding these points? One point can be in anywhere from 0 to infinity, any positive point, but the second point is always, at least the distance between them is at least 1. Oh, sorry, 1 over n naught, at least 1 over n naught. Okay. Now note that where does this x naught lie? So there, no matter what delta you choose, I'll choose some natural number. Where does this lie, x naught? If we divide it, what is the first value? 1 by 2 minus 1 by 2. Second value 1 minus 1 by 4. Third value 3 by 2 minus it's an increasing function. Okay, and when delta is small enough, n naught is obviously greater than 0. So basically these points, after a while, they lie in outside 0. Okay, so I think this is how we do it. And okay, so I want to just show you one example of my this question of closed interval to interval, closed interval. So now this question is there. Okay, so now we already know, so like let's say from I in R2 this is closed. So we already know f of I is an interval. This we have done. Okay. Now image of the closed real interval is bounded. This is tricky to understand. So if this is a closed interval, then its image is bounded. Why is that true? Can I think about this? So let's say, suppose Fi is not bounded. Okay. That means there exists a sequence in the interval such that f of xn mod goes to infinity as n goes to infinity. Right? If something is not bounded, I can always find a sequence such that it goes to infinity. But since AB is a closed interval, that means there exists a subsequence of xn such that xn converges to some x. So since f is continuous, here comes the continuity. That implies but if f of xn converges to infinity, no matter what subsequence you choose, that will also converge to infinity. But there will reach a contradiction. Okay. Now that it is bounded, right? What you can do is you can take a supremum of this, supremum and infimum of f of I. Okay. So now the supremum, when there is a supremum, let's say supremum of f of I is some d, right? What you can do is you can always have a sequence such that it converges to d. Okay. Now xn has a subsequence which converges to it, again using continuity. F of xnj converges to d. and f xn of j converges to f of x. Again, from a there exists a subsequence. Hence, f of x by uniqueness of limit f of x is d. So you can reach the supremum. So basically what we are saying is, on a closed interval, not saying bounded. For instance, this is also a closed interval. This is an interval, it is closed, not saying bounded. This also has a maxima and a minima. So for any closed interval, this is an interval which has a f of I has a maxima and a minima. So if it's an interval and there is a maximum and a minimum, that implies I is what? F max, F min to F max, and hence it is closed. Is this clear, Karthik? It's not. It was not very like. I think it's clear, right? If something is not clear, I can explain it again. Yeah, you're audible. Yeah, go ahead. Yeah, okay. Yeah. Yeah. Okay, okay. Let me explain once again. Okay. What I'm saying is, we are clear on this, right? That if one second. Right. So so if okay, yeah, just one second. So if f of I is not bounded, let's say, right? For example, I can give an interval, not a closed interval, but an open interval. For example, for tan x, right, minus pi by 2 to pi by 2. That is not bounded. Whenever something is not bounded, you can choose a sequence which is going to infinity, right? Yeah. So f is what? So there are some. This is r. Over here there is some I, and this is some f of I. And when this is there, this is a sequence that is going to infinity. It will be corresponding to some sequence in I, right? For some xn, there will be some f of xn, and that will go to infinity as n goes to infinity. What I'm saying is, since I is closed interval, right? A closed interval means compact, because what we can say is, okay, not compact, but for any closed interval, what you can do is either it's compact or it is going to infinity, right? How can you write a closed interval? Either you write like this or like this. This is clear, right? Only these three are example of closed interval, right? There cannot be any other thing which can be called a closed interval. Is that clear? Yeah. So when this is the case, it's compact. In this case also, what you can do is, whenever there is a sequence from minus infinity to a, you can find a subsequence which converges. So xn is some sequence, we don't know what it is. What we are saying is we can find a some subsequence which converges. What do we mean by converges? In a real number, every sequence will have a subsequence which converge, right? No matter on a interval like this. And what we mean by convergence, it will converge to some x in I. Okay? When this happens, when x and j converges to some x, when this is what we have been doing in this class, right? No matter what sequence, a subsequence is a sequence as well. If a sequence is converging and if f is continuous, that implies this. So x and j converges to x, that implies f of x and j converges to f of x because of continuity. And x is in I. So f of x is also in, f of x is well defined. Now if one sequence goes to infinity, any subsequence will go to infinity. So this was supposed to go to infinity, but it is going to some f of x. F of x is not infinity, right? F of x is well defined, a real number. So there is a contradiction. So hence this cannot, what? Yeah. F of I is bounded. So this was the assumption and we reached a contradiction. So hence this cannot be true. Bounded. First we showed that it is bounded. Now we want to show once it's bounded, we can take an infimum or a supremum. Anything that is bounded is a bounded set. In real number, we can take an infimum and a supremum. Now let's call supremum to be D. Again, the same logic that f of xn, we can always find a sequence which goes to D. It's a supremum, right? You understand the definition of supremum? That for every epsilon, I can actually subtract something and this will be greater than, there exists a number such that this is true. If I am taking a sequence on f of xn. So that means I can always find a sequence which goes to supremum. All I have to show that it touches the supremum. So that means again this there is an xn, right? F of xn goes to D, so there is an xn. Again, same logic that there is an xn, there is a sequence inside all these three. I can always find a subsequence which converges to some x. I don't know what x that is. These are called existence proof. So that implies, because of the continuity again, that f of x and j converges to f of x. But since f of xn was converging to D, any subsequence converges to the same value. This is also true. That implies D is nothing but f of x and x was in I. So basically a supremum is reached from the interval. So basically what we are saying is any closed interval has a maximum and a minimum. An interval, not a closed set. Closed interval. Any closed and bounded set also has a maximum and a minimum. So that was called extreme value theorem. This is the modified extreme value theorem. So a closed interval may not be bounded. Closed set and bounded. These two have a very good property, a continuous function always attains a maximum and a minimum. Not just bounded, it attains the maximum and a minimum. For example, when we are doing 10x, right? 10 inverse x. 10 inverse x, the graph goes like this, right? This is bounded. The f of, so 10 inverse of r is bounded. But max and min are not achieved. It's an interval, but it's not closed. It's a closed set, but not bounded. That's why it's not achieved. To understand the intricacies, like everything is not just there, everything has its purpose. If you're doing in controls theory or like anything, if you want to do, if you're doing in higher dimension, these are things right now, even in engineering or in any field, they're important to understand. Okay, you cannot just say that there exists a minimum, there exists a maximum. People are doing simulations right now and they're like, okay, you do some simulation, you get some result. It could completely be a garbage if you don't know if the existence and these kind of proofs that okay, if there exists a maximum and a minimum. And this is a very, very important idea, especially this closed and bounded set. This is the key. All the things are generalization of this. All the minimization problem, the whole of the engineering is generalization of this. Whenever you're finding a maximum or a minimum, any kind of optimization, this is the central idea. This kind of idea is adapted universally, and like you increase in some way, generalize it in some way. These are very important ideas. Okay, so let me do one more question. Okay. I will prove this. This was said in the, I think, lecture notes, but I will prove this in general. And if we approve that, we solve this question. This question. This was the claim that I made. And if this is true, then f is uniformly continuous on 0, 1. Then obviously f is uniformly continuous over here as well. But this is not true. This is true. We have showed that in general for R this is not true. Again, this is wrong. But this is also true. If this is true, this is also true. Okay? So I'll prove this claim and we'll finish our class with that. Question: if F goes from R to R is continuous, then F is uniformly continuous on K in R with Ks compact. We'll prove this and we'll be done with today's class. Okay. So since f of R to R is continuous, let K in R be compact. So now what you can do is, if you take an x, let x not belong to K, then for every epsilon greater than 0, there exists a delta which depends on x naught and epsilon, such that and this is a compact set, right? I will do with the sequence here. So there exists xn converging to x naught such that f of x naught converges to so let's say x was some complex set, there's a point x naught over here. I want to find an interval that covers it. That means just 1 second. No, the idea is I would just want to generalize this in special case of R. Okay. So this is the idea that is if I have x naught, for every epsilon greater than 0, there exists a delta because of this epsilon and x naught greater than 0 such that okay, yeah, so what I can do is x naught is in K, right? Let x naught be not on boundary. Okay, so x naught is inside an open set. So what you can do is you can find a delta such that this point, all the y's inside this, like all the x minus y less than equal to delta epsilon x. This, what does this imply? That f of x minus f of y is less than epsilon. So for all these y's, this is true. Now if there is a compact set, what we can do is we can cover it by these open intervals. Okay, so no matter what point it is, I can cover this by open intervals such that these open intervals, union of these open intervals covers K. And compactness, what it means is, like, it's a generalization of the sequence, is this: there exist a finitely many balls or intervals. So if you want to understand in terms of a compact, this is, let's say this is a compact set, right? What I'm saying is, for any given epsilon, they need not be disjoint, since it is, so let's say the length of the whole set is bounded, right? So let's say the length of, this is the length of a compact set is less than equal to m. Okay, so if I take m over epsilon open intervals of epsilon length, they will definitely be covering this K. Okay, so once that happens, right, what you do is choose, so there are these deltas which depends on n. So if you have like delta epsilon, this is delta epsilon, what you can do is choose the smallest one. So I will actually, so what I'm seeing in my notes is in a higher dimension. I will try to do this in terms of sequences and maybe do it in next class. That what exactly happens in terms of real numbers. Sometimes it's harder to understand things if you're written in a higher dimension in terms of real numbers. So okay, so thank you for watching this. That will be all for today, and I'll see you in the next class.